Okay, please, Davide.
Okay, so I'm going to talk about some project that I've been working on for a while in collaboration with Costello and Yagi, and some follow-up project with Derushenko that should be coming up soon. And both projects should be coming up soon. The basic objective of these projects is to understand the role of Tooth operators in the four-dimensional Chern-Simons theory that Kevin Costello has introduced as a tool to study integrability. And in particular, I would like to explain how these Tooth operators are related to the notion of Q function or Q operator in integrability. Sorry, I'm having trouble now. Into the next slide. Okay. So the structure of the talk is very simple. I will just review four-dimensional Chern-Simons theory and try to remind you of what are the relationships to integrability and in particular to the Youngian. I will review the role of Wilson lines in four-dimensional Chern-Simons theory. They are something that allows you to build transfer matrices associated to finite dimensional representations, and to build, they are the basic building blocks also that we call that you use to engineer a spin chain in four-dimensional Chern-Simons theory. And then I will introduce Tooth operators and their relation to Q functions. In particular, I want to explain how the TQ relations are related to the Witten effect in the gauge theory, and the relationships to the quantized Coulomb branches of three-dimensional and equal 4 gauge theories. And perhaps at the very end of the talks, a relationship also to interfaces in four-dimensional and equal 4 supermeals. So, four-dimensional Chern-Simons theory. This is a bit of an unusual theory. It's a modification of the standard Chern-Simons theory, which in a sense promotes the it promotes one of the three directions of three-dimensional Chern-Simons theory to an holomorphic direction. So it's a theory defined in 4 dimensions. It's holomorphic topological. It's topological in 2 of the directions that I'll call x1 and x2, and depends holomorphically on the third direction, on the third and fourth directions, which I'll combine into a z and a z bar. To define the theory, you really only use the components of the connection along the topological directions and the anti-holomorphic direction. And the action is pretty much the Chern-Simons action built out of these components, wedged with the 1 form, make it 4 form, and then integrated over 4-dimensional space-time. So there is, see, this choice of a very specific 1 form in the holomorphic direction is part of what makes it not logical. Sometimes it's useful to integrate this action by parts and think about this as a, sorry, I'm hearing a strong echo. Anyway, to think about this as a sort of a position-dependent theta angle, a theta angle which depends holomorphically in 2 directions of space-time. Now, you might feel uncomfortable about the fact that this theory uses some sort of complexified constraints on your gauge fields, throws away a complex combination of 2 components of the connections, and has an action which doesn't look very real. So you can think about this in 2 ways. So Kevin originally used this action just to define perturbation theory as a way to produce Feynman diagrams, which had some good properties if you want. You can also try to think about this action as being used to define a sort of a contour path integral, where you integrate on a certain contour inside the space of complexified fields. And there is a whole technology developed by Witten to think about contour path integrals, analytic continuation of path integrals. And this technology can be applied to 4-dimensional Chern-Simons theory. And a way to apply this technology is just to identify the 4-dimensional Chern-Simons theory as a 6-dimensional supersymmetric Yang-Mills theory on an omega background. the omega background localizes the six-dimensional theory to 4 dimensions, and the localization a la Nekrasov leaves you with an action, which is this 4-dimensional Chern-Simons action. The relationship to 6-dimensional Socratic Mills is also useful because it provides a chance of UV completion of the theory within string theorem theory. Indeed, another way you can think about the 4-dimensional Chern-Simons theory is that it's the volume theory of some branes in some topological string theory, or in some twisted supergravity background, alla Costello. All of these perspectives are potentially useful. We will, in this talk, they will provide only one piece of input, although quite useful. But for most of the talk, it's perfectly fine that you just think about things perturbatively. Perturbation theory in H-bar, computing Feynman diagrams. And you get expressions that often resum to actually good functions of H-bar, although sometimes with peculiar properties, peculiar locality properties. So, what are the basic observables in this theory? As in Chern-Simons theory, there are not many local observables, that not really point-like observables. Although you can still define a sort of a BRST complex of local observables, which I might be able to discuss after the break. Just if somebody is interested in causal duality. But otherwise, the most natural observables to think about are Wilson lines, much as in Chern-Simons theory, standard Chern-Simons theory. In standard Chern-Simons theory, the Wilson lines are topological. You can just wrap them along whatever paths you want in 3 dimensions, make knots, make links. In this holomorphic topological setup, the Wilson lines naturally wrap the topological directions x1 and x2, and they sit at some very specific location in the holomorphic direction, up to a certain framing anomaly, which I'll discuss momentarily. Can you hear me well? Just make sure. Okay.
Yes.
So to define a Wilson line, the first thing you can try is to just do the usual path order exponential of the gauge field along some direction of space-time. So I take, say, the A1 component of the gauge field, and I integrate, I contract with it some matrices acting on some internal finite dimensional degrees of freedom, and integrate along the path order exponential along the x1 direction. This definition is classically fine in gauge invariant, but there are quantum gauge anomalies which pop up at all orders in perturbation theory. And the idea is that you can fix these anomalies by adding higher counter terms to the action. Notice that I highlighted the holomorphic dependence of the gauge field, in the sense that because the theory is holomorphic topological, the dependence on the other directions of space-time really drops out. When you try to build these higher counter terms, using derivatives in the topological or anti-holomorphic direction will be useless because it will be BRST exact. But you can take derivatives in the holomorphic direction. And so you can have counter terms when you take some derivative of the connection in the transverse direction, and you contract with some other matrices acting on the internal degrees of freedom. So to build these counter terms, you need sort of an infinite collection of matrices which generalize the generators of the gauge group.
Sorry, a small question. What is the gauge group here?
What for now is just whatever you want. Later on, I will mostly focus on ADE, although it's not a necessary constraint. At least the embedding in string theory I know is for ADE theories. I would have to think a little bit if you can embed non-ADE gauge groups. I should think about it. Correspondingly, when we encounter the Yangian, we'll encounter the Yangians of ADE, the Yangian of ADE groups, which is the simplest to define. Perhaps somebody in the audience can remind me if there is a good Yangian for non-ADE groups. I'm a little bit ignorant of some of these matters. But for now, let's say you're looking at some ADE reductive gauge group or gauge algebra. Now, if you want to cancel the anomalies order by order in perturbation theory, you need to impose some constraints on this infinite new collection of matrices. Essentially, their commutators have to be certain polynomials in the matrices. And Kevin proved that these relations are precisely, these commutation relations are precisely commutation relations of the Youngian. So the idea is that to build a Wilson line in this four-dimensional Chern-Simons theory, you need to have a representation of the Youngian. And in a sense, the very existence of the Youngian is related to the existence of four-dimensional Chern-Simons theory. So a lot of the properties of the Youngian, like the existence of coproducts, the associativity of coproducts, the existence of R matrices, and so on and so forth, can all be justified sort of almost geometrically from the existence of this holomorphic topological theory. And again, I can discuss this further after the coffee break. But for now, there is sort of this sudden emergence of the Youngian from the very pedestrian problem of defining a good Wilson line in the four-dimensional Chern-Simons theory. I find this quite striking. Now, you might find it amusing that, or peculiar that you find potential anomalies, gauge anomalies at all sorts of loop orders. I mean, usually when we are more used perhaps to situations where the gauge anomalies appear at one loop. But part of the way you can understand this more physically, if you try to go in the more physical setup of six-dimensional Yang-Mills theory, these anomalies, if you try to sort of follow back what these anomalies are in the six-dimensional Yang-Mills theory in omega background, there are obstructions to defining a supersymmetric Wilson line coupled in six-dimensional Yang-Mills coupled to this omega background, which means coupled to supergravity essentially. So in the physical theory, these possible gauge anomalies were really supersymmetry problems with the supersymmetry. So problems in finding supersymmetric counterterms on your Wilson line and coupling to the supergravity fields. And so somehow this technology of Costello must be expressing all sorts of complicated neuronormalization theorems in these supersymmetric theories coupled to supergravity. And I think it's an aspect of that has not been developed yet properly, not just in this example, but in general. So Kevin has a collection of results where there is some twisted theory like this, which has a unique collection of counterterms which are built order by order in perturbation theory and often unique. So he can write things like that which don't even look renormalizable, right, because they have Agar derivatives, but in which all the counterterms are fixed uniquely by the symmetries, by the gauge invariance. And you gotta wonder what sort of normalization theorems these represent in the original theories. I should mention, for example, there is another result that he has where he says that the Kodara-Spencer theory, say, is a unique perturbative quantization if you require it to be coupled to holomorphic Chern-Simons theory. This seems to be some statement about, again, to 10-dimensional supergravity and the counterterms of 10-dimensional supergravity. Perhaps there is some theorem that says that if you want supergravity to be coupled to supersymmetric Yang-Mills, this fixes some counterterms. Anyway, let me move on. Sorry for the aside, but I just find expressions like this really interesting, and the emergence of interesting algebraic structures on these Hager loop gauge anomalies. Quite interesting. Perhaps I should mention here, right, another point. So as you can see, once you start introducing arbitrary amounts of derivatives in the z direction, the precise location in the z-plane perhaps gets a little bit fuzzy. Or if you want, saying that the Wilson line is at z or at z plus delta is a bit conventional in the sense I could just redefine my t's to absorb the translation in z. If you know the Youngian, you know that if you have a representation of the Youngian, there is a sort of a automorphism that shifts the spectral parameter of that representation. And by looking at how this t is transformed and you try to shift z, you can identify the position of the Wilson line with the spectral parameter of the representation of the Youngian. A final point I should mention, although I will not use it much, is that although the theory is classically holomorphic topological, there is an interesting framing anomaly. So if you try to bend your Wilson line in the topological plane, you risk creating new gauge anomalies, which are cancelled by making the position in the holomorphic plane vary as well. Essentially, if you try to bend the Wilson line by some angle, it has to shift in the holomorphic coordinate by that angle times z times h bar times some constant. In particular, you cannot just take the plane and draw a circular Wilson line, because as the Wilson line bends around, it comes back at a shifted position in the holomorphic plane. So this four-dimensional Chern-Simons theory doesn't really have things that look like knots. And this sort of framing anomaly ultimately was used by Costello and Witten and Yamazaki to explain a lot of interesting properties of the representations of the Youngian. There are all sorts of relations, like TT relations, Hirota relations, where you get, which are a sort of a deformation of classical Lie algebra relations. Where you say, I take two representations, the classical Lie algebra, I multiply them, and I get some sum of irreducible representations. I try to do the same with representations of the Youngian, and on the right-hand side, I get more or less the same sum, but the spectral parameters get shifted in some funny ways. Well, these shifts can be often justified in terms of this framing anomaly. Somehow, to fuse Wilson lines into some composite, you need to give them some bending, which turns into shifts of the spectral parameters. The simplest example is when you sort of try to fuse two matrices into the identity representation. If I have two Wilson lines and I want to bend it to annihilate it, I want them to annihilate each other by bending one of them. This bending translates into a certain shift of the spectral parameter. So to find the identity, I need to take the tensor product of the two representation and representation bar with some shift to the spectral parameters.
Can I ask a question
about
this point? So this framing anomaly, is there a natural interpretation from the 6D super Mills point of view?
Because it's proportional to h bar, it's a bit subtle in the sense that h bar is the Nekrasov deformation parameter. So if I went in the six-dimensional Mills theory and I turn off the Nekrasov parameter, the framing anomaly would also disappear. So, right, it must have something to do with supersymmetrical coupling to the omega background. But, okay. So, perhaps you're familiar with the way to compute things in three-dimensional Chern-Simons theory in axial gauge. When you work in three-dimensional Chern-Simons theory in axial gauge, the propagator only goes in the direction of your axial gauge, which means that if you have some complicated knot and you try to compute the expectation value of the knot, you can essentially project it down on the plane and you only get contributions when two strands cross, because the gauge field managed to propagate from one strand to the other only when they cross in the projection. This gives the state some representation of Chern-Simons correlation functions. In this holomorphic Chern-Simons theory, there is something similar going on. there is a sort of holomorphic axial gauge where the gauge field only propagates along the holomorphic direction, and everything remains very local in the topological direction. So that again, the effect of a path integral over the gauge fields. Can you see my arrow? Yeah, the effect of a path integral over the gauge fields just results in a local matrix that is inserted inside your Wilson lines. So if you take an intersection of two Wilson lines in the four-dimensional transformers theory, you do all of your Feynman diagrams, you sum them up. The result is just some very local interaction placed at the intersection of the two Wilson lines in the projection. I mean, the Wilson lines are not intersecting; they sit at z and z prime in the holomorphic plane. But if you project them down to the topological plane, you get also an effective interaction at the intersection. And you can convince yourself easily that this effective interaction must be some kind of an R matrix. Essentially, because if I take configuration of three Wilson lines, because of topological invariance, I can just move one of them from the left to the right. They sit at different values of z, so there is no risk of them hitting each other when I do this. But once I integrate away the gauge fields, if I do the calculation on the left picture, I get some combination of these local interactions contracted along the lines with matrix indices contracted along the lines. If I do the calculation on the right, I get a different contraction, but they're trying to compute the same thing, so I should get the same answer. And so I get immediate Yang-Baxter relations.
Sorry, David, but these Yang-Baxter relations, the one you show as a Yang-Baxter diagram, scattering, these are projections to the topological plane, right?
Yes, that's correct. So I have three lines, they sit at three values of z, which are the spectral parameters, z, z prime, z double prime. They can move freely around.
Sure.
But if I go in this gauge and I integrate away, I do the path integral of the gauge fields, I'm just left with contracting the indices after doing the path integral. The path integral of the gauge fields just give me some purely local contributions to each of the vertices, which don't really talk to each other. Okay, so this is how you realize that you can get R matrices, you can get integral systems out of four-dimensional Chern-Simons theory. And this R matrix is just the standard R matrix associated to the Yangian. And perhaps I can let me elaborate on that for a second and then go back. So when you have your Wilson lines, right, and you integrate away the gauge fields, the gauge fields interact with the internal degrees of freedom of the Wilson line in a way that is mediated by these matrices. So the result of this path integral is just sums of products of these matrices acting on the internal degrees of freedom. And the path integral itself doesn't actually know what representation I was talking about. It just really uses the fact that these matrices represent the Yangian. And so because of that, the result of the path integral is just some universal R matrix in the Yangian times the Yangian, specialized to the specific representations. So I want to stress this, so this picture really tells you that the Yangian has a universal R matrix. And if you consider a picture which I did not draw, where you take Wilson lines and you just collide them in the topological direction, you can also convince yourself that the Yangian has a coproduct, and that matrix intertwine the coproduct in the two directions. Now, if you want to engineer a spin chain within four-dimensional Chern-Simons theory, there is an obvious strategy. You take your topological directions to be a cylinder. You take a collection of time-like Wilson lines in some representations and at some positions in the holomorphic plane. And then you take an extra space-like Wilson line, which wraps around and is closed. So the result will be a collection of R matrices with internal representation with the indices for the internal line contracted in a sequence, and then taking the trace over the representation R. So you get exactly what the transfer matrix for a spin chain. The trace of a product of a collection of L operators.
Or could I ask why can't you contract the loop to a point then, or just a bit confusing?
Well, sorry. So until now I was on the topological plane, and I even said I cannot close a loop in the plane because it bends. But here, instead of working on a plane, I'm really working on a cylinder.
Hmm.
So this space-like Wilson line is wrapping the cylinder. It's not bending. It's just going straight. That's why it's
I see.
if you try, if you try to use geometries on the topological plane which are not flat, as you try to transport the Wilson line around, you would have to keep track of the local bending. So this framing anomaly, I think really means that, although the theory is supposed to be homomorphic topological, if you want to do topological manipulations, you need to sort of pick a local, an auxiliary metric to define the Wilson line and the angle of the Wilson line. And then this deformation will move the Wilson line in the Z-plane. I think the question, what exact backgrounds can the four-dimensional Chern-Simons theory be coupled to quantum mechanically is perhaps not being spelled out properly yet. But for now, I'm just keeping the topological direction flat, and I'm even keeping the holomorphic direction flat. There are variants of whatever I'm saying which apply when the holomorphic direction is replaced by a C star or by a torus or by some other geometries. You can get a variety of systems, not just spin chains. There are ways, for example, to get relativistic integrable quantum field theories using similar constructions and get defining transfer matrices or Lax matrices in these quantum field theories by using pretty much the same pictures. And everything I'm going to say about Q functions will carry over to all this broader collection of systems. Right, so anyway, so here you can define a transfer matrix. You can even put an holonomy, a gauge holonomy around the circle to put a twist in your trace. And obviously, these transfer matrices are going to commute with each other. So if I take two space-like Wilson lines, I can move them across each other without any singularity. So, okay, any questions until now? This was a review of how to build spin chains in four-dimensional Chern-Simons theory. Okay. Now, when you work with the Youngian and you work with spin chains, there is a variety of other things you can do besides transfer matrices in finite dimensional representations.
Oh, sorry, could I ask, is there some natural interpretation of eigenfunctions from Chern-Simons point?
That's a bit trickier. I'm not aware of a natural interpretation. And I've been quite curious about the interpretation of, for example, beta roots in this setup. And again, I don't have a clear understanding. Although now I'm going to introduce Q functions, still have not been able to use them to understand what the beta roots are in this setup. I should also say that because the four-dimensional Chern-Simons theory is this sort of contour path integral, analytically continued theory, speaking about the Hilbert space of the theory is also a little subtle. You might have to make extra choices to talk about the Hilbert space. Here somehow in this particular setup with flat space, flat topological and holomorphic directions, the Foddy Chern-Simons theory has no degrees of freedom really. And so the Hilbert space just gets contributions from the time-like Wilson lines. But in more complicated situations, it gets interesting.
But then, so about Q functions, so in principle, you can build T transfer matrix in any representation, and then you can think about Q function as T function in some limit when the representation becomes like bigger and bigger in your shift.
Absolutely, yes, yes. I was gonna get that in a moment. But yeah, you're correct. So using the Yangian, you can get a variety of commuting transfer matrices which are not associated with dimensional representations. A general strategy is to take any algebra morphism from the Yangian to some other algebra which is equipped with a trace. Then the universal matrix is going to give you some matrix applied to a finite dimensional representation, and this using this algebra morphism gives you some matrix of elements in the algebra. You just take the product in the algebra, take the trace, you get your transfer matrix for which is still going to commute to the finite dimensional transfer matrices. A classical example is to take the morphism from the Yangian of SLN to the universal enveloping algebra of SLN, quotiented by the center, so that you fix the Casimirs to some fixed values. This gives you a transfer matrix which depends on a variety of parameters. There is the spectral parameter, and there is the value of you choose for the Casimirs. So you get in total n parameters. And this transfer matrix, there is a way to recombine these parameters into essentially something that looks like n spectral parameters. And this transfer matrix behaves as a product of simpler blocks, which are called Q functions. Although the representation itself does not break into co-products of representations.
So can I?
Yes.
Yeah. How is it that you get the fact that the Yangian representations are often reducible with respect to the group you started with? How do you get the Wilson lines? Take a Wilson line in a representation that's not actually quantizable because it's not a Yangian representation.
Well, it means that although classically I could define a Wilson line, quantum mechanically at higher loops, there are gauge anomalies which I cannot correct. So if there is a representation of your gauge group which does not lead to representation of the Yangian, well, then it just means that the corresponding Wilson loop is broken. It cannot be fixed by counter terms.
Okay.
And differently, if you ever had multiple lifts to the Yangian representation, these multiple lifts will be different ways to define the quantum line. Okay, so now you could ask if there is any natural way to engineer some of these more complicated transfer matrices within four-dimensional Chern-Simons theory. In a natural way. Now let me just say a few more words about Q functions, just to remind I'm not sure there is somebody in the audience which has not encountered Q functions in an integrability seminar, but let me still remind you. So there are different ways you can stumble into Q functions as you study integrability. One of the ways, perhaps you're studying just the beta equations for your spin chain, and you realize that it's convenient to think about functions whose zeros are the beta roots. You might be studying the recursion relations satisfied by transfer matrices, and realize that it's convenient to define some objects which satisfy relations like this. For example, in SL2, you can say that you might want to look for solutions of difference equation, where one of the coefficients is the fundamental transfer matrix in the doublet representation of SL2. Or perhaps you might want to solve the Hirota relations in terms of some simpler, write down a generic solution of Hirota equations. And so for SL2, you would say that which are recursions satisfied by transfer matrices in various representations of your Yangian. So for example, in SL2, you could say, okay, I take the transfer matrix in spin J, and there is a natural way to decompose it into some kind of quantum determinant-ish expression involving two Q functions. Or perhaps you say, okay, I want to take now the transfer matrix associated to a Verma module of SL2, a more infinite dimensional and complicated object, and you might discover that it behaves in many ways as if it was the product of two things, again, the product of two Q functions. And the way you might realize that is if you take the transfer matrix for a Verma module. So here, sorry, I should have written, Z1 and Z2 are sort of the spin of the Verma module plus minus the spectral parameter. And one way you might discover this factorization is that if you take the coproduct, if you take the product of transfer matrices for two Verma modules, you discover that they have extra symmetries you wouldn't have expected, where you can exchange Z1, the Z1s of the two modules or the Z2. Anyway, so all of these relations might make you think that there is some extra representation of the Yangian, which with transfer matrix is a Q function. This is not quite true. The Q operators do not come from Yangian representation, although you can define something called a shifted Yangian, which kind of allows you to access them directly. But otherwise, you can just take representations like the Verma module, which gives you a product of Q functions, and send one of the spectral parameters to infinity, which just removes one of the factors and leaves you with one Q function. And this limiting procedure is pretty much how you get the shifted Yangian from the Yangian anyway. Okay, so these Q functions are these sort of mythical objects which you encounter all over the place in integrable systems. And they appear in spin chains, they appear also when you study, as I was saying, integrable quantum field theories. And they are very often a key to solving the problem. So you can derive the Bethe equations from the Q functions. You can derive TDA equations maybe from, anyway. All sorts of interesting properties of integrable systems become more transparent when you look at Q functions. So we wanted to find a concise description of these Q functions in the four-dimensional Chern-Simons theory.
Yeah, I'm just conscious of the time.
Yes.
So I'm wondering if at some point it might be good to have a little break.
Yeah, absolutely, absolutely. I started a bit late, so perhaps I was thinking of doing another slide.
Perfect.
Okay. So the way you get Q functions for the four-dimensional Chern-Simons theory is by studying 't Hooft lines. So what are 't Hooft lines? 't Hooft lines are disorder defects. They are line defects in a four-dimensional gauge theory, which are defined by prescribing some singularity in the fields in the neighborhood of the line. You know, in a standard abelian gauge theory, you might want to think about them as electromagnetic duals of the Wilson lines. In an abelian theory, more precisely, you can define them by just saying, I want to have some magnetic flux on a sphere that surrounds the line. And so trying to make the definition precise, you get a 't Hooft operator. In a non-abelian theory, the definition is a little bit more subtle because there is not a good definition of magnetic flux, really. So what you do is you take whatever definition you had in an abelian theory and you embed it in the non-abelian theory. So you say, okay, to make it 't Hooft loop in the abelian theory, I had to prescribe some singularity in the fields. Well, for the non-abelian theory, I'll just prescribe the same singularity modulo gauge transformations. And so the basic data which labels the 't Hooft operator is just pretty much a way to embed a U1 inside your gauge group. So you take a U1 subgroup of your gauge group and you just set the magnetic flux for that U1 to be non-zero, to be some charge, some value on a sphere surrounding your loop.
So in view of what you said before, can one model 't Hooft lines by Wilson lines and some weird representation and taking some limits?
Usually not, but in Chern-Simons theory, it does sometimes happen that disorder operators turn out to be the same as Wilson lines. So indeed, I will describe momentarily how to give an alternative definition of the 't Hooft lines, which involves a local one-dimensional system coupled to your, in a sort of a Wilson line-ish way. But in a generic gauge theory, tooth lines and Wilson lines will be completely different. And the precise definition of a tooth line is tricky. It's theory dependent, especially for non-abelian theories. First of all, because you need, even in an abelian case, you need to find a viable singular solution which has flux on a sphere. And this might depend on your equations of motion. Like you want the classical singular solution which has a flux around your line, and then you say that you do a path integral over fields which approach that singular solution near the line. And then in the abelian theories, there is an extra subtlety, that is that those words I said, modulo gauge transformations, you really need to understand carefully what sort of gauge transformations you're talking about. So to define a Wilson line properly, you really need to figure out what is the classical phase space of singular gauge fields that you consider, and then find how to quantize it. And I'm not sure anybody has ever done it, even for a non-supersymmetric Yang-Mills theory properly. But in supersymmetric theories, with the help of supersymmetry, things are simpler. People have definitely defined successfully tooth operators. And you can do calculations in the background of a tooth operator. And similar, you can do it in four-dimensional Chern-Simons theory. So we studied these tooth loops in two different ways. One is by really figuring out the phase space and how to quantize it. And the other one is by sort of learning from the embedding in side string theory to find an order definition of the defects as where you couple the theory to some one-dimensional system, auxiliary system. And perhaps I'll discuss that after the coffee break. But for now, all I want to say is that once you define these tooth operators properly, you can just use, you can wrap a tooth operator in a special direction, you get something which is precisely behaving as a Q function. So all these sort of properties of the Q functions, especially the recursion relation, take a very clean interpretation in terms of Wilson line, or in terms of line defects and their fusion. And the truncations of the Yangian, this collection of algebras that you use to define the corresponding representations emerge naturally. So for example, if you take a configuration of two tooth loops in SL2 gauge theory, which should give us two Q functions, which we know we can get from coupling a Verma module to using the Verma module representation of the Yangian. Well, the Verma module is obtained by quantizing pretty much T star CP1, and the phase space for the Chern-Simons theory in the presence of two tooth lines is precisely T star CP1. So the four-dimensional Chern-Simons theory with toothed lines builds automatically a phase space whose quantization is the correct representation of the Yangian. You would need to define the corresponding product of Q functions. Okay, so this is a message I want to give until now.
Just before the coffee, to clarify, will you build 2 to the n, where n is the rank of the symmetry of such constructions, or your construction for the product of Q functions?
So there is an interesting subtlety which has to do with the charge at infinity, but you can get 2 to the n. Although the construction is sort of, if you're suppose I look at SL2, right? So if I take a product of Q functions with some pluses and with as many pluses as minuses, then you can realize that product is representation of the Yangian, and you get that on the nodes. And if you have a different number of pluses and minuses, you need a representation of the shifted Yangian, but correspondingly there is a four-dimensional Chern-Simons construction which gives you a phase space whose quantization is indeed the shifted Yangian, a truncation of the shifted Yangian.
Plus
So-
or minus, you mean the flavor of the Q function, kind of, right?
Yes, yes. So yes, you can get should to the n answer in SL2, or n to the k in SLN. In general, for an ADE gauge group, there is an elementary Tooth operator for each node of the ADE quiver. So you get something analogous to a Q function for each node of the ADE quiver, and you get a good phase space for each collection of these Q functions.
Okay, thank you. So should be 10 minutes?
Well, I think we were aiming for a little bit longer to allow people questions, but let's see how it evolves. But yeah, so I guess thanks, Davide, for the first part, and everyone can grab a cup of coffee and start chatting informally and asking questions, I guess, and so on.
So we normally pause the recording. So that
Sure, let's pause the recording. Yeah.
Okay, so right, let me discuss dionic lines for a moment. So line defects can have both magnetic and electric charges. Essentially, you turn on you pick an embedding of U1 inside G to define the magnetic charge. This breaks the gauge symmetry at the node to some subgroup of G, to some H, and you can dress the magnetic line by a Wilson line for H. So, for example, if you have an SU2 gauge theory, your tooth charge would break SU2 to U1, and then you can put a Wilson line under U1. So it's important that Wilson line, whenever you have a dion, the charge for the electric charge is a weight for H, not a weight for G. So, for example, in SL2, I can have two dions with magnetic charge 1 and electric charge 1 or minus 1, while there is only one Wilson line. There is an interesting effect, which is called Witten effect, which is that the electric charge of a dion changes if you change the theta angle of your theory. So the quantization of charges of line defects is really shifted, so that the charges of the dion look like an electric charge plus the theta angle times the magnetic charge. Now, if you remember, one way to think about for Dirichlet-Simons theory is a theory where the theta angle is variable as a function of the holomorphic position. So as a consequence, if you change the position of your dion, your electric charge will be shifted by the magnetic charge. So if your electric charge is aligned to the magnetic charge, you can eliminate it just by moving your dion around. So now let's take a simple.
How to the shift?
Yeah, that's right. You shift by a multiple of H bar.
Oh.
Which I wrote it here schematically. It depends on the charges. Okay. And on the theory, on the specific gauge group. But for example, you can do the following exercise. Suppose you take a Wilson line in SL2 and you fuse it to the tooth line. Intuitively, because the gauge group is broken from SL2 to U1 on the tooth operator, my Wilson line will break into two abelian Wilson lines, one with charge 1, one with charge minus 1. So the result of such a fusion is in general a sum of two dions with charge 1, 1 and 1 minus 1. But then I can use this relation to recast it as a sum of tooth operators with positions shifted by an amount H bar or minus H bar. So this should remind you of the TQ relation. If I wrap these lines around a circle and I cross some other Wilson lines, the Wilson line will give me a T function, the tooth line will give me a Q function. I'll discover that TQ is Q with a shifted argument plus Q with a shift, with opposite shift.
Sorry, in this relation, normally one of the terms should have quantum determinant as well, not just unity.
Well, it's a matter of how you normalize things.
Yeah.
So, you know, if you're in SL2, you would like your ideally you would like your arm matrix to have quantum determinant 1.
Well, if you want Q to be polynomial, I guess there is no.
That's right. There is a bit of a tension. So I'm happy to renounce Q being a polynomial. So if I work in the gauge theory, the Wilson lines produce the T functions with a very specific, or their matrices with a very specific normalization, such that the quantum determinant of their matrix is 1, pretty much because I can take one of these Wilson lines and bend it around and annihilate them. So this means that the T function I'm using here differs on the one that you usually use by some products of gamma functions, which sort of fix the normalization of T.
As
and
well
the
as
Q function also. Sorry?
Yeah, that's what I said. As well as Q, it also differs by some.
Absolutely. So yeah, I need to put some gamma functions in Q, some gamma functions in T, and then all the prefactors you're talking about disappear. And this is what you should be getting from the gauge theory. And those gamma functions have all sorts of interesting poles and multiples of H bar, whose physical meaning is really obscure to me. Because in the local quantum field theory, you wouldn't really expect to see poles away from the location of your defect. But this, if you expand, but perturbatively, these gamma functions have no singularities. They just have a nice perturbation theory in H bar. But somehow, when you try to resound this perturbation theory into something non-perturbative, you get these funny poles. And the physical meaning of those is still unclear to me. There's a bit of a non-locality somehow in the holomorphic direction. Anyway, so this sort of reasoning explains things like the TQ relations within four-dimensional Chern-Simons theory. Now, I would like to discuss a bit more the proper quantum definition of these 't Hooft lines. So, something that helps a lot is that the phase space of the four-dimensional Chern-Simons theory is as a complex manifold is pretty much the same as the space of solution of Bogomolny equations, where 't Hooft operators just correspond to Dirac singularities in the Bogomolny equations. This is a very well studied system. It gives you nice complex symplectic mod-like spaces. The precise phase space you get depends on the charges of your 't Hooft operators and on how much magnetic flux escapes at infinity. Now, it just so happened that these manifolds of solutions of Bogomolny equations with some boundary conditions coincide with the Coulomb branches of some three-dimensional N=4 gauge theories. So three-dimensional N=4 gauge theories have some spaces of vacua called the Coulomb branch, which are complex symplectic manifolds, and happen to coincide with these phase spaces if you take gauge theories in the form of quivers, quivers in the shape of an ADE diagram. This fact is not a coincidence. So if you go way back to the six-dimensional Yang-Mills setup and embedding in string theory, there are, so a 't Hooft line in the four-dimensional Chern-Simons theory lifts to a 't Hooft volume in 6D super Yang-Mills, something still has dimension 3. So there are three-dimensional defects in six-dimensional super Yang-Mills. These three-dimensional defects have sort of two dual descriptions. One is as actual 't Hooft lines, as disorder operator, and the other is as order operators, where you couple the 6D theory to some three-dimensional N=4 gauge theory. And the second order perspective is quite useful. It's quite useful because when you turn on the omega big ground to reduce this three-dimensional defect to a one-dimensional 't Hooft line, you know exactly what's going to happen because people have studied the omega deformation of three-dimensional n = 4 theories, even quite recently. So the omega deformation.
Is this some intersecting brane?
Yes,
secretly?
in type A, you can just think in terms of the 3 branes crossing the 5 branes. If you want to get type D and type E, you need to work a little harder. But 60 amines for type D and type E can be lifted to essentially little string theory and then embedded. So there are ways. And yes, one gets to this argument that right, so turning on the omega deformation in this three-dimensional n = 4 theory is a very specific effect. It deforms the algebra of functions on the Coulomb branch to some non-commutative algebra. And this is sort of the algebra of local operators that you have available on your one-dimensional defect to couple to the 4-dimensional Chern-Simons theory. So because everything is done in string theory with branes, everything can be coupled to supergravity, and everything can be coupled to this omega background. So somehow, whatever supersymmetric counter terms you need to define the coupling of 6D superior mills to the 3D defects and to supergravity must convert into valid couplings on this line of Chern-Simons theory, where these T's are going to be some specific local operators in the three-dimensional n = 4 theory. And so you get the prediction that somehow there should be a relation between the Youngian and the quantized Coulomb branch of these 3D n = 4 theories. And indeed, this has been discovered at some point that the quantized Coulomb branch of ADE quivers is a truncation of the Youngian. So if you give me a quiver in the shape of an ADE group with unitary groups at the nodes, you pick some ranks, you pick some number of flavors, you define the Coulomb branch, you quantize the Coulomb branch in a canonical way, which mathematicians have, such as Braverman, Finkel, and Nakajima have discovered a few years ago. You get an algebra. This algebra admits a map, nice surjective map from the Youngian, or from a shifted Youngian, depending on the charge at infinity.
Could I ask something, maybe not directly related to what you said, but so what makes it special, the point z = 0, for example?
Nothing.
Because as we discussed about this poles of gamma functions, right? So your Q operator will have analytical properties which are specific for z = 0 and plus nh.
So in that case,
where does it come from? Where is specific?
It's not really z = 0, it's the location of the other defects. So somehow these poles tell me that when I look at this configuration, I get singularities not just when z hits zi, which I would have expected, but in general when z minus zi is a multiple of h bar, which is funny. Right, so using let me say again what I'm trying to say. There is a classical phase space which I can compute from four-dimensional Chern-Simons theory, which is the solutions of Bogomolny equations. But then to define the quantum theory, I would need to quantize it. And it's not obvious how to do so. Luckily, it coincides with the Coulomb branch of this 3D n = 4 theories, which has a canonical quantization. And even more luckily, this quantization is also implemented by just the same omega background, which I used to define for the Chern-Simons theory. So if I take the 6D theory coupled to the 3D theory and I omega deform everything, I will land with the 4D theory coupled to a 1D defect. 1D defect which supports this quantum Coulomb branch algebra. And for consistency of the whole picture, it must be that this defect with the quantum Coulomb branch algebra on it can be coupled to the 4D Chern-Simons theory. And indeed, there is a very nice canonical map from the Youngian which encodes these couplings. So again, there must be some huge amount of information here about supersymmetric couplings in these higher dimensional systems. But anyway, this means that in practice, if you tell me, okay, I want to have 5 Tooth operators with these charges in this gauge group, I can just write on a quiver, take the BFN construction, and out comes an algebra with a trace, which actually is equipped. Another nice thing is these quantum column branches are equipped with traces in a very natural way. And so I can use these traces to define some transfer matrices, which turn out to be products of Q functions corresponding to the Tooth operators. So here is just saying what I just said. I'm supposed to go forward. So I take a collection of Tooth charges as some Tooth operators, some specific position Zi. I get a quantum column branch algebra, which depends on these positions. From the point of view of the 3D gauge theory, these are mass parameters. This quantum column branch algebra has a canonical map from the Yangian, and it has a nice collection of traces, which are actually labeled by the vacua, or by massive vacua of the 3D theory. And so I can use this data to produce the transfer matrix. This will be a product of Q functions. Which Q functions depends on the choice of trace. Mathematicians has also studied a lot the category of highest weight modules for these algebras. It's called category O. And I assume that all of the QQ and TQ relations you might like can be interpreted just in terms of asking how this category O behaves under coproduct. It's actually nice that there is a coproduct on these algebras, which is compatible with the coproduct of the Yangian. So there's more detail. Now, I wanted to mention sort of a reverse application of this construction that I've been studying with Nicola Dedushenko, which is that, so until now I was using the 3D theories as a tool to arrive at integrability statements, but you can go backwards. There is something called the sphere partition function of 3D Nicholson theories, which happens to be a very particular trace on the quantum column branch. And it is of independent interest. I mean, when you study these theories, you might want to be able to compute correlation function, protected correlation functions on the sphere of some column branch operators. And this relation to integrability allows you to express these correlators as transfer matrices of the spin chain, which is kind of fun. And this is true for 3D Nicholson theories, and it can also be used to study interfaces in 4D and Nicholson Superman mills. So you can, if you know explicit expressions of Q functions acting on the states of the spin chain, you can use those expressions to learn about correlation functions of these 3D or 4D Nicholson theories. Okay, I think I said more or less all I wanted to say. I don't know how am I doing with time.
You're doing perfectly, I think. So let's thank Davide for this really very nice talk. And well, maybe I'll ask. I won't stop recording just yet. If there are any questions that want to be recorded.
Yeah, could I? So I just missed the beginning. So how do you make this Wilson lines gauge invariant, because they have ending points, obviously?
No, they don't. No, they don't have endpoints.
Because like you want Hamiltonian or transfer matrix to be acting on some vector with indices, right? So how does it work?
Somehow the endpoints are at infinity. So
yeah, because like actual T should be an operator acting on some vector space, which would represent this indices, right? So
yes.
I
mean, what you should imagine is that you're just taking the path integral of the gauge fields and leaving your Wilson lines there, so that the one-dimensional systems there. So now you have some vector space. Which
contracted between some ground state in some sense, right?
yes, that's right.
Not transfer matrix as operator, but some expectation values on some simple states.
What's the difference?
Well, is that you don't control which states it acts on, right? So
No, you do. I mean, you have a Wilson line, right? A Wilson line is a quantum mechanical system with a finite dimensional vector space coupled to your gauge theory. You integrate with the gauge theory.
Yeah, but I mean,
the quantum mechanical system.
This diagram is just a number; it's not an operator. That's what I mean. So it's the same way when you say Q operator, it's probably a Q operator acting on the vacuum because it gives you a number, right? Then.
No, it gives you a matrix element between any states in your representations. So in the past, I can pick any state in my product of representation arise. I can pick any state I want in the future, and then.
Like another related question probably is in order to get the spectrum or whatever from Q system, you also need to control very well the analytic properties, as you know. So Q relation more or less follow from but then the analytic properties is some information you add on top of that. So how much control is that?
So I don't think perturbation theory is enough for that. I still have the hope that if one understands the non-perturbative completion of this picture properly, one could derive those analytic properties. But I do not know how.
Yeah, other questions?
So for example, in the case of integrable quantum field theories, I can study T functions or Q functions using IMODE, the IMODE correspondence. And you can see that somehow if you identify this parameter H bar in the IMODE correspondence, then you do perturbative expansion in H bar, you reproduce what you expect from Fovicki-Simons. But all the sort of analytic properties that you would use to define a TBA, to find the TBA equations, are invisible because they involve shifts by H bar.
Yeah, it's like also computing a Hirota equation just by computing averages of Wilson lines. You will never perturbatively see Hirota as such. Right?
That's true.
Okay, so maybe I'll turn off the recording now and we can ask more informal questions.